What's up, guys, and welcome to this video. Okay, so we're still on kinematics. I've gone through distance versus displacement, velocity versus speed, and acceleration, instantaneous velocity as well. And now we're going on to these graphs. Okay, so these graphs are fairly simple and they're always pretty much easy to read and understand, but you need to get the basics correct. Okay, so we have three different types of graphs. So we have displacement time graphs, we have velocity time graphs, and we have acceleration time graphs. Okay, and all of these are related in some way, and we'll see how they are related in a bit. But okay, so displacement time graph. So what does that look like? Okay, so we have displacement on the y-axis in meters and time on the x-axis in seconds. Then a velocity time graph, what does that look like? So we have obviously velocity on the y-axis in meters per second, and we have time again in seconds. And an acceleration time graph, I'm sure you've guessed it, we have acceleration in meters per second squared, and we have time in seconds. Okay, and all of these graphs are vectors. Okay, so the graphs can exist in the positive or the negative. Okay, and how that changes why they change is dependent on our sign convention. So we need sign conventions for all these graphs. Okay, so what does that mean? So that means if I choose upwards or if I choose to the right as being positive direction, whenever my person or thing is moving to the right, it is going to go in the positive. Okay, the same if we have the velocity being positive that way, then when I'm increasing my velocity in the rightwards direction, that's going to increase. Okay, if I had negative towards the right, then as I move away from some reference point, I am going to the negative direction. Okay, but we're going to do some examples and go through all of that. Yeah, okay, don't forget to put your 0 points in. Sometimes teachers tend to take marks away for not putting that in. So yeah, with that being said, okay, so what is a displacement time graph? So basically it shows how the displacement is changing with time. Similarly, the velocity time graph shows how the velocity of an object is changing with time, and the acceleration time graph shows how the acceleration is changing with time. Okay, just a heads up, expect a pretty long video here. Okay, so what is our first scenario? Okay, so our first scenario that we can have is we can have a stationary object. Okay, so what does that mean? For a stationary object means not moving, right? The object is not moving. Okay, so if it's not moving, then that means the displacement is not changing. Okay, if it's not moving, that means the velocity is equal to 0. Okay, if you're not moving, then you can't have a velocity. Okay, and then lastly, similarly, the acceleration is equal to 0. Okay, so what do these graphs look like? So displacement meters, time in seconds. Okay, I'm going to start leaving out the units soon. I'm just putting them in to emphasize the fact that you need them when you draw your graphs, but possibly not when I draw my graphs, because I'm not getting marked. Okay, so what does this look like? Okay, so if let's put in a little example. You are waiting for a bus 10 meters from the bus stop. Okay, and you wait for 20 minutes. Okay, so basically what's going to happen is we're going to choose the distance away from the bus stop as being positive. So we know that at time equals 0, you are 10 meters away from the bus stop. Okay, we also know that at time equals 20, or not 20 actually, we want time in seconds, so that's 120 seconds. That's not right, that's 1200 seconds. Okay, let's make it 2 minutes actually. Okay, so 120 seconds, you're still 10 meters away. Okay, and this entire time you have not moved, so you're going to just have a straight flat line. Okay, the velocity time graphs for a not moving object are fairly simple. You are not moving, so your velocity is exactly the same, and it is 0 for the full 120 seconds. And the acceleration time graph looks exactly the same. Okay, I'm going to do these in red, hopefully you can see them better. Okay. Okay, and the acceleration time graph, same situation, there is no acceleration, so therefore our graph is just flatlining on the axis. Okay, until 120 seconds. Okay, so that's the first scenario when we have a stationary object. Okay, so the second scenario, let's say number 2, is the motion. We have constant velocity. Okay, so if we have constant velocity, what can we say? So constant velocity means we're traveling at the same speed, right? Oh, sorry, not traveling. Yeah, it means we're traveling at a constant speed, basically. Okay, that's pretty obvious, so let's take that out. So what we can say is that the position of the object is changing at the same rate. Okay, so what does rate have to do with? Okay, so rate, whenever we saw the rate, it meant change of something over change of time. Okay, and that is usually associated with our gradient. Okay, so for a constant velocity, remember velocity equals change in displacement over change in time. So our position is constantly changing at the same rate. So that means our gradient must always be equal to our gradient of our displacement time graph. So therefore the gradient of our displacement time graph must be constant. Okay, so I hope that makes some kind of sense. Okay, so let's try drawing the graphs. Okay, so we have displacement time, we have velocity time, and we have acceleration time. Okay, so our position time. Okay, so let's use the same scenario. So example, when the bus arrives, you walk to it, or walk the 10 meters at a constant velocity in, let's say, 2 seconds. Okay, so the first question we have to ask ourselves is what does, okay, actually the easiest thing to answer right now is the velocity time graph. Okay, because we can calculate the velocity. Okay, so velocity equals change in displacement over change in time. So we have a 10 meter change in displacement over 2 seconds, which is equal to 5 meters per second. Okay, and we're traveling at a constant velocity. That means the velocity time graph is plateauing. Okay, so it takes you a total of, so at the 0 point, and it takes you a total of 2 seconds. Okay, next I am going to go to the acceleration time graph. Okay, so if you're traveling at a constant velocity, it means that there cannot be a acceleration. You're not accelerating, because then you'd either be speeding up or slowing down. Okay, so again, our acceleration time graph is just a nice plateau for 2 seconds. Now we have to ask ourselves the difficult question, not so difficult, of what does the displacement time graph look like? Okay, so I know at 0 seconds I have not left, so I am at the origin, and I know that at 2 seconds I am 10 meters away. So basically I have 2 points. Now the question is, how do I join this? Okay, but I've kind of already answered this, because I said the gradient of our displacement time graph, this point right here, the gradient needs to be a constant. So to have a constant gradient, we have a straight line graph. Okay, we have a straight line graph, and our change in gradient, or change in displacement over change in time, is equal to our velocity and is equal to a constant. Okay, so I hope that makes sense to you guys. Okay. Okay, now we have some other topics to discuss. Okay, so what happens when we have acceleration? So when the velocity is changing. Okay, so when the velocity is changing, it can either be increasing or decreasing. Okay. Sorry. Okay, so it can either be increasing or decreasing. Okay, so when the velocity is changing, we have acceleration. Okay, so acceleration cannot equal 0. Okay, and when the velocity is changing, the velocity okay, we're also going to deal with constant acceleration. Okay, most likely deal with constant acceleration. Okay, so yeah, let's go over an example. Let's sway away a bit. Example. Okay, so we let's say a car is accelerating at 5 meters per second for 10 seconds. Okay, draw the velocity time graph and all the other graphs. Okay, distance squared, meters per second squared for 10 seconds. Yeah, okay, so I'm happy with that. Okay, so let's draw out the situation very quickly to make sure everyone understands. Okay, so let's say it starts at rest. Let's say it starts, so the car starts at rest. Okay, so initially it is at rest. Okay, then for the next 10 seconds, it starts off pretty slow, but it speeds up. That's what accelerating means, right? So it speeds up as it goes on its journey. Okay, so let's start drawing some graphs. So we have our displacement time graph, we have our velocity time graph, and we have our acceleration time graph. Okay, so I know that it's okay, we should also probably say a car is accelerating at a constant. Five meters per second. Okay, cool stuff. So whenever we see a constant 5 meters per second, the easiest thing per second squared, sorry, the easiest thing is we know our acceleration at time 0 is 5, and we know that our acceleration at time, 10 seconds is also 5. And if we know that it's constant, so what we have is we have our straight line graph, well, plateau, and it goes for 10 seconds. So what does our velocity look like? Okay, so so we know this car starts at rest, right? So it starts at 0 meters per second, but at some 10 seconds, Okay, it's no longer 0, it's at a different value, right? So what value is that? So we want units of velocity, which is equal to meters per second, right? We have acceleration of 5 meters per second squared, and we have time at 10 seconds. So if we multiply these two, okay, if we multiply these two, we can get units of meters per second, because these seconds will cancel each other. Okay, so if we multiply, we end up with 50 meters per second. So basically, we know that at time 10, the velocity is 50. Okay, and okay, so when we have constant acceleration, our gradient for our velocity time graph, so with constant acceleration, okay, so our gradient of velocity time graph must equal a constant. Okay, so what we have is we have this point 0 and point 5010 being joined by a straight line graph. Okay, now the question is what's happening with our displacement time graph. So our displacement is 0 at point 0, and at point 10 it's no longer 0. So now we're looking at the velocity time graph. I know okay, so I'm just going to do it. I'm going to tell you that the displacement equals the area of my VT graph. Okay, so the reason for that is I want displacement, and displacement has units of meters, right? And I've got velocity in units of meters per second, and I've got time in units of seconds. So if I multiply these two equations, they cancel out and I'm left with meters. Okay, so what's the area under this graph? So the displacement S is equal to a half times the base times the height. So that is 250, if I'm correct, meters. Okay, so at time equals 10, I'm at 250 meters. But remember that my velocity, because I'm accelerating, I'm getting faster and faster. Remember, so it starts out slow. So it starts out slow and then it speeds up, right? And it gets faster and faster. And right at the end is where I'm fastest. So that means our gradient needs to start out slow, right? Because it's only doing, let's say, 2 meters in the first couple seconds. In the first couple seconds, it's only doing 2 meters. But then it's speeding up, it's speeding up, it's speeding up. And right at the end, if we look at the end, the change in the last 2 seconds, it's done maybe 10 meters or 20 meters or 50 meters. Okay, so basically we have a graph where we start out slow. The gradient, think about the gradient. You start out with a slow gradient and you're speeding up, so the gradient gets steeper and steeper. Okay, so I hope that makes sense. Okay, so those are basically the 3 situations you'll really come across. There are other situations that you might come across, but those are the 3. Okay, so now I want you to just try and understand how we go from one graph to the other using information from the previous graph. Okay, so I'm just going to draw in a random graph. So let's have constant acceleration. Let's have a change. So constant acceleration, and we're going to have something like this. Okay, so if I have a displacement, okay, so first of all, let's see what happens when I get my areas. Okay, so everything has to do with gradient and area. So you have to ask yourself, what's happening with the gradient and what's happening with the area under my graph? What are these 2 quantities telling us? Okay, so the gradient of acceleration time graph. Okay, so let's look at acceleration time. Gradient of acceleration time graph is change in acceleration over change in time. Okay, if we look at the units, let's look at the units on orange. So I'm left with meters per second squared divided by seconds. So that comes out as meters per second cubed. Okay, we're not really used to anything there. So we can actually say that the gradient of acceleration time graph doesn't really matter. No one really cares what that quantity is. Okay, there's not a lot of meaning. But what about the area? It's not the blue. What about the area? Okay, if we look at the area of our acceleration, to get the area, we're looking at acceleration times time, right? Let's look at units. So we're left with meters per second squared times seconds. Okay, so if we carry that out, these seconds cancel, and we're left with meters per second. Okay, and this is units of velocity. Okay, so if we have an acceleration time graph, our gradient is basically meaningless, but our area under that graph, area tells us of our velocity. Okay, so the area is equal to our velocity. So if we have an acceleration time graph and we need the velocity, we can just calculate the area under that graph. Okay, similarly, let's do the same thing for the next two graphs. Okay, so if we look at our gradient, we're looking at rise over run, or whatever you want to remember it. So it's change in velocity over change in time. So let's look at our units. Okay, so change of velocity is in meters per second and time is in seconds. So we're left with units of meters per second squared. And whoa, that is units of acceleration. Okay, so our gradient, let's actually do it here. Our gradient is equal to our acceleration. Okay, so if we have a velocity time graph and we need the acceleration, we calculate the gradient. Now let's look at area. So area would be velocity times time. Okay, let's look at units. Velocity is in meters per second and time is in seconds. So if we multiply those two, we get out, these two cancel, so we're left with meters. And meters are units of displacement. Okay, so units of displacement. So if we have a velocity time graph and we calculate the area, our area is equal to the displacement. Okay, and finally, if we look at our displacement time graphs, if we look at our gradient, what we have is change in displacement over change in time. So that's units of meters per second. The units are meters per second, and that is units of velocity, is it not? Okay. And then if we look at the area, is equal to displacement times time. If we look at the units, those are units of meters times seconds, meter second. Okay, we're not really used to that, so it's meaningless. So basically, the gradient, our gradient tells us our velocity. Okay, so you can always come and use these out of first principles like I've done, or you can just remember something. I don't recommend it, but sometimes it's easy just in an exam or something, you don't need to think. So the way you do it is you write displacement, velocity, acceleration. Okay, so if I start at my acceleration time graph, okay, so you either work with arrows that way or arrows in the opposite direction. Okay, so if I start with my velocity time graph, okay, and I want my displacement, then I follow the arrow and I get to my so I follow my arrow, so I need to calculate the area. If I start at the velocity time graph and I want to calculate the acceleration, then I follow that arrow and I use my gradient. Okay, similarly, if I start at my acceleration time graph and I want to calculate my velocity, I follow the arrow and I use my area. Okay, so that's one way of just a quick reminder of how to use this. But obviously, you can just use it by first principles like I did before, or you can remember this. So to the left is area and to the right is gradient. Okay. Okay, I just want to go ahead and prove some of these things that I did, and I think the best way is to prove it using this right here. Okay, so I have my velocity time graph. So I'm going to start at my velocity time graph. So I'm starting here. I want to calculate my acceleration, so I calculate my gradient. So looking at my gradient, so I want gradient is equal to change in velocity over change in time. There is no change in velocity, so my acceleration is 0. And that's exactly what I got here. I got a 0 acceleration. If I want to calculate my displacement, I've got to use the area, right? I'm going to the left. So I calculate my area. So what's my area under this graph? Area equals 5 times 2, which is equal to 10 meters. And that's exactly what we calculated before. And similarly, if I want my velocity, we did it here, we calculated the gradient. So if I have a displacement time graph, so I start off with a displacement time graph and I want to get to my velocity, I calculated the gradient. And that's what I did here. I wanted the velocity, so I calculated the gradient. If I did that, grad is equal to change in y over change in x, or let's say change in s over change in t, so we have 10 over 2, which is equal to 5 meters per second, and that is that value right there. Okay, so yeah, a bit of a long video, not so bad, I guess. In the next video, I will be doing some examples, probably. If I don't do examples, then just go check out the IEB questions on kinematics. All of the questions are pretty much the same thing, but I'll probably do an example here and there. Okay, thanks for watching, guys. I hope you found this useful.